Alright, so today we're going to go through Module 8, Inquiry Question 1. The syllabus outcome we're looking at is investigate the processes that lead to the transformation of radiation into matter that followed the Big Bang. If you actually have a look, so the title obviously for this lesson is the Big Bang Theory. We are investigating how radiation became matter. Remember, when we refer to something as matter, it means something of mass. So how did we get from the process of having just energy, and how did that energy then become mass there? As you would know, from here to here, we already talked about before, it's to do with mass energy equivalence. So that's kind of the idea there. Textbook reference is given down below, as you can see, right here. Okay, just before we go into how radiation became, or energy became matter, I just want to go through the quick idea is, how do we know how much power the sun is generating? Now, the simple formula that we have here is capital P, so that's power output. Okay, that's given by the intensity. So that's the intensity of the sun that we see at a particular distance for the area of that sun. So from our distance, how big does the area of the sun appear to us, and what's the intensity at that distance there? So there's that. Okay, so that's our area. Now the main thing you need to remember is R is the distance between the two objects. So if I have the sun here and I have the Earth here, we're looking at from one center to another center like that. That's our distance R. Another thing that we will talk about a little bit is the standard model of elementary particles. This model basically shows you what we call the elementary particles, so things that can't split down anymore. You might have heard this story before when we first talked about the atom. The atom is not an elementary particle because it can be broken into electrons, protons, and neutrons. As a matter of fact, protons and neutrons are also not elementary particles. They can be broken down further into what we know as quarks and leptons. The only one out of the three that is an elementary particle is actually the electron. Okay? All these particles you see here, okay, these are particles. They also have an antiparticle. So for the electron, we talked about before, its antiparticle pair is the positron. Same mass, opposite charge. Okay. The next we also said is hadrons. Now that's what protons and neutrons are. They are hadrons. They can be made up of three quarks, three antiquarks. Could be made up of a quark and an antiquark. So that's what we have. If you actually look at the structure of the neutron, it's made up of two down quarks and one up quark. A proton is made up of two up quarks and two down and one down quark. Okay, so that's what we have there. So we're looking at what process in our universe did we start seeing these things form? Okay, so what is the Big Bang Theory? And there's a little bit, so this is the most accepted explanation of how the universe first began. Okay, there is a little bit of misconceptions that can come from what we mean by the Big Bang. So we're going to cover that first, and then we're going to look at what we believe from evidence happened in our universe. So the Big Bang Theory proposes that the universe began with an event where an enormous amount of energy began to expand from a point where we call the Singularity. So here I've tried to avoid to say a single point, because the understanding is it's not just some fixed dot in space where the universe began, but it's this small three-dimensional space that we had initially, which we call the Singularity, and all the matter, all the energy was really condensed. So we had a lot of energy clumped together and causing this great expansion. So when this expansion occurred, there was an enormous amount of energy that was released in all directions of our universe. The universe started at an intense heat and it began to cool as we got this expansion. The universe was also initially compressed to a very small volume, and it expanded, which we call the Big Bang. So what's actually known as the Big Bang, it's not an explosion, it's an expansion of energy. Okay? So that's kind of what a lot of people might get confused with. What we say is the bang is actually the great expansion of energy, and then obviously later when matter is formed, also matter. Okay, so a very small volume, we'll change that from 0 to a very small volume that began this expansion. So what do we mean by this singularity? So singularity refers to the point at which all the scientific theories, all the scientific principles, laws, mathematical models, all these equations we've been talking about in physics break down, so they don't work. Okay? So that's what we mean by singularity. At this point in time where nothing that we've developed explained anything. Okay? By extrapolating back in time, we would see that there was a point where gravity hadn't had enough time to pull mass objects together to form stars and galaxies. We would find that the universe was really hot, there was no neutral atoms, so we had these ions or nuclei flying around, and protons and neutrons are dissociated into elementary particles. Basically what that means is protons and neutrons didn't exist at the singularity point. Okay, so there's our expansion there. So what we're going to look at is investigating the processes that led to the transformation of radiation into matter. We're going to look at specific timelines, and as you can actually see from our diagram here, we can see that from the Big Bang, the two main elements of the periodic table formed was hydrogen and helium. As a matter of fact, when the Big Bang was ongoing, when it first formed, there was about 75% hydrogen to about 25% helium. What we do know is all the hydrogen that we have right now in our universe originally came from the Big Bang. So that kind of tells you the story of how all things came to be. As a matter of fact, you might even be able to see the Big Bang, the supposed point at which the Big Bang occurred, is about 13.7 billion years ago. So all this hydrogen and helium that we have now, or the hydrogen that we have, that, originated from that long ago. So there you go. Okay, so what I'd like you to do, obviously, is you can always have a look at this video here to help you begin your understanding. But let's look at a couple of questions. Question 1, it says, the first atoms formed about 380,000 years ago after the universe began. What were the elements of these atoms and why did it take so long? So, like I said, at the very beginning, we had 75% hydrogen and we had 25% helium. Now the reason why it took so long, okay, why did it take so long? It's because of the heat. Okay, heat, the temperature or the amount of energy at the start when the universe first began was really high. So high heat was high, that meant that it was difficult to form atoms, difficult for particles to come together. Now remember what I said earlier, when we had a lot of energy, a lot of the fundamental laws that we had at the beginning, that didn't really work. So gravity wasn't working, gravity wasn't pulling these particles together. So if gravity wasn't really there, then obviously you can't have these quarks binding onto each other. The reason why we did eventually form is because the expansion caused cooling in the universe. So it's this expansion, as you know, as you get further and further away from the source, the amount of heat or energy given off is lower because there's more space for it to cover. So cooling down, and so gravity could pull particles together. So like I said, we initially had our quarks and leptons. Those came together to form hadrons, which is your protons and neutrons. That forms your nucleus of the atom. And then later on, as more cooling occurred, you got electrons also coming into the equation. Right, someone summarized 4 brief points about the ideas in the Big Bang and evolution of the universe. Let's have a look at some of the main key points. So we said that at the beginning, the fundamental laws of physics did not exist. So that's really important to understand. All the laws we talked about did not exist at that point in time. There was a great expansion of energy. During that expansion, that's when we saw the conversion into mass. In that transformation, that's where we got our quarks and leptons. And then as we expanded further, so further expansion and cooling of universe led to the formation of hadrons and then obviously the atoms. If you have a look at the actual timeline, there's actually quite a lot of different things to take into account in this timeline. We have actually a lot of things happened within the first second. So if you actually have a look, this is actually broken down here like so. So within the first second of that Big Bang event, we already had all our fundamental forces. We already had the elementary particles. So it's actually a really quick event. Okay. From about 3 to 20 minutes, we got nuclear fusion, nuclear synthesis. So if you recall, that's when we're forming the nucleus. So protons, neutrons, electrons existed, but it would take another 380,000 years before atoms formed. The reason being, the expansion was so far, things couldn't kind of jolt back together, but let's give a bit more context. So the earliest data that we know from scientists of the existence of the Big Bang is through this thing called the cosmic micro background. Okay, you might have seen this picture a couple of times, but it has a really interesting backstory. So 2 scientists were investigating with these satellite dishes, and they were getting these interference signals, and they weren't really sure what was it from. They found out that there were some pigeons sitting on the satellites. They had these really big satellites, and they were trying to clean out pigeon feces. They did the experiment again, and they still detected this, and what they actually found was this interference pattern they were seeing was actually the same microwave background that would show the very first formations of the atom. So let's just talk about what's happening in the early universe. So 10 to the minus 43 seconds, what we call the Planck Error. At this point in time, no laws of physics existed, didn't really explain anything, and this was just after or just before our singularity point. This is also where we assume that space and time, this idea began. Right after that, we get this expansion. So the biggest amount of expansion occurred just after the Planck Error, what we call the Grand Unified Era. So gravity becomes separated from other forces of physics. Remember, there's 4 fundamental forces. We'll show in a second. The strong nuclear force, the weak nuclear force, and the electromagnetic force were still existing as one force. We got the formation of bosons. So bosons are things that carry forces. So gluons, photons, these are in a way your radiation. So there's that. These particles, the bosons, exert fields or forces that help generate interactions with particles. Okay, so that's what's happening there. Okay. After a bit more cooling, we get that the gravitational force and strong nuclear force became separate things. The electromagnetic force and the weak nuclear force were still the same thing. So let's just put this idea together. So this, obviously, gravity is an attraction of mass particles. Okay, the strong nuclear force is the force to hold the nucleus together. So force holding nucleus. As a matter of fact, we know that the strong nuclear force is exerted by the neutron. So that's actually the function of what the neutron does, to hold all those protons together. And then we call this the Electroweak Error. The reason being, obviously, the electromagnetic force and the weak nuclear force are still inseparable. Because we have a strong nuclear force, we do start seeing, elementary particles trying to form larger particles there. The weak nuclear force and electromagnetic force, like I said, are still coexisting. At this stage, photons could convert their energy into particle-antiparticle pairs that would annihilate each other and reform photons. So, we talked about this before. The very first beginning of which we're seeing energy mass equivalence is already happening here. So what's happening is we have two gamma rays that would collide, okay, and that would cause the formation of an electron and a positron, so the particle-antiparticle pair. What we also know, we talked about previously, is this concept of particle annihilation. So the proton and the electron are going to then come back together again, and they're going to collide and make gamma rays, two gamma rays. So if you actually have a look, as we said before, the amount of energy generated from these two particles colliding and forming gamma rays gives us that amount of energy. Okay? So that's one of the consequences of mass energy equivalence that we're seeing right there. Okay? Now something really interesting happens. During this period of time, the universe is thought to have experienced exponential expansion, reaching 10 centimeters across. So we had a really small point, and then it expanded really rapidly, but it's only 10 centimeters at that point in time. So you can see the universe was still very small. Mind you, not a second has passed yet, so that's kind of the reasoning. So this rapid expansion is necessary to prevent the initial universe collapsing back on itself into a black hole. Remember, we do have gravitational force now, so if the expansion was big enough, gravity, or the force of gravity, would pull everything down and then would collapse everything. But the expansion would continue. If we continually had expansion at this really rapid rate, exponential rate, there wouldn't be no formation of atoms. Okay? The reason being, obviously, there would be not enough energy to move around. Okay, as you can see, actually, we've done some major cooling here. Initially, this is how much temperature we had, and then we're cooling down to that there. Okay, now something really interesting happened, and that's for some very strange reason. During the particle-antiparticle annihilation, when the gamma rays broke, every so often, in a very rare opportunity, there was one additional particle in comparison to an antiparticle. So we had this additional particle over this antiparticles. So at some point they weren't eliminating each other anymore. You just had two pairs that were sitting there. And that's quite important because one, we have electromagnetic force coming out and the weak force. And the consequence of this is as the universe kept on expanding, because there was these additional particles being formed, then by expanding, everything cools down, less energy, less collisions are happening. So we're forming particles now. That radiation isn't, those particles are no longer going back into radiation, they're stuck as particles as the universe expands further. Okay, you have our little timeline. So all that happened within the first second. We haven't even really talked about the protons and the neutrons yet. All right, we're still kind of stuck here in this current slide point. Okay, so the formation of matter. Let's look at how everything came to be. So once we had the electromagnetic force and the weak force, the Higgs boson, one of the famous discoveries back in 2013, it enabled particles to have mass. Okay, so that's kind of coming into special relativity, but the actual thing that helps these particles to gain this mass is because of this Higgs boson here. Okay, so from that, fractional of a second to the 3-minute mark, now we find that more elementary particles begin to form. These are our quarks and leptons. Now remember, like I said, the reason why these particles are forming is because every now and then we have this mixed match of more particles than we have antiparticles. Universe is expanding, so less likely they're going to come back into each other because they're moving further away. These quarks would then form our protons and neutrons. We call this combination of quarks the hadrons. If you actually have a look at our nucleosynthesis, so at this point here, up to about the 3-minute mark, we've already formed the basic proton and neutron, but we haven't got to the point of making the hydrogen nucleus or the helium nucleus just yet. Okay, so the formation of matter. Okay, now the universe is expanding. Okay, and we have a lot of matter particles now, so they're all clumped around in a similar area. This is where gravity can start doing its work. So a thing what we call nucleogenesis, the existing new atomic nuclei in the nucleus can form with the nucleons. Okay, so we have these protons and neutrons coming together because of the strong nuclear force, and now we can get nucleosynthesis or nucleogenesis, the very first formation of the basic nuclei or nucleus that form our periodic table. So these were sort of the main ones that we're seeing here. Okay, hydrogen 1, hydrogen 2, hydrogen 3, helium 3, and helium 4. Okay, so after that, another 300,000 years occurred. The planet or the universe was still a bit too warm for electrons to bond with the protons and neutrons. But as that cooling occurred, electrons moved slower, so they had less energy to move around. So the electromagnetic force was strong enough now, because these electrons are moving slower, to be attracted into the positive nucleus. Okay, so that's great. That's forming the very first atom. So it took at least 30,000 to almost 400,000 years since the singularity point for us to form the very first helium atom. And then while we're at it, another eternity later, we got our stars. And now at this point, obviously, it took quite a long time. There was what we call the dark age of our universe. So for about, can't quite remember what the exact date was or exact timeline. Let's just have a quick look. So about 1 billion years ago, that's when we started forming giant clouds that would later turn into the galaxies and stars. So we had 300,000 years to wait to get our first atom. It took us another 1 billion years to get the first stars and the universe that we see here. Obviously now we have all this dust of atoms where gravity can kind of pull them all together. Okay, so we have pockets of unevenly distributed matter existing with this enormous amount of empty space after the particle-antiparticle annihilation, which, as I said before, there was more particles than antiparticles. The denser regions would exert a greater gravitational attraction, so that's going to pull all these things together. So when we have denser material, it's going to pull everything towards the densest part of the cloud and then compress together, and wow, you have your stars, you're shining in the universe. Okay, so these stars are dragged in and we get that. And so we have a spiral of stars at that center point. That gives us our universe, or our galaxy, sorry. So that's how, we got our stars, that's how we got our universe. Okay, so if you want to talk about like what's happening here, we have this. So all the big activity, the formation of radiation turning into particles or matter, that happened within a second of the beginning of the Big Bang. 3 minutes at that point there, we began to see fusion of basic nuclei forming the isotopes of hydrogen and helium. 380,000 years, that's the remnants of the microcosmic or cosmic microwave background. So just radiation of all that energy being released with the formation of the basic atom. Then we went through a period called the Dark Ages, where there was no light, essentially, hence why we call it the Dark Ages. 200 million years, according to this diagram, so not 1 billion years. 2 billion years, that's when we started forming stars, and then obviously later on galaxies. And then we get to our modern day today, 13.8 billion years. Obviously, depending on the diagrams, they will give you a slightly different decimal of how old the universe is. That's just because of when they're published. So there's that. So what's next? What's after that? Okay. We have two predictions. The universe could continue to accelerate in an outwards direction and eventually gets too cold, deep freeze, and all the galaxies just kind of have not enough energy to survive, or the acceleration decreases and then we have what we call dark energy overcomes gravity and dark matter, and then we have gravity pulling sort of things back together. So we're not really sure which way the universe is going to end, if it ends at all. So there's a couple of theories that we have at the moment. Okay, so let's have a look at some of the questions. Define an elementary particle. Well, an elementary particle is, particles that cannot be divided. So you could say they're the fundamental particles cannot be divided, you could say. In quark theory, what is the difference between a meson and a baryon? Now, both of these are actually hadrons, but if you actually have a look in between, what we can see from this diagram here is the meson is made up of a quark and antiquark, while our baryons are made up of 3 quark combinations. Okay, so there's that. Alright, so describe the formation of the matter in the early universe. We can let you have a go at that. And the inflation period lasted a currently short time. What might have been a consequence had it lasted longer? So like we said before, if it expanded really rapidly, there wouldn't be enough time for all the different particles to condense together, And so if we didn't form the atoms, we wouldn't have actually ended up with galaxies and stars, and we wouldn't get civilization that we know today. Okay? So that kind of ends our summary of the Big Bang Theory, or the timeline in which the Big Bang Theory, let me say that here, the journey in which the Big Bang Theory occurred. Okay, so that's a little nice summary to you. If you want to check out other links of this particular inquiry, we talk about nucleosynthesis, we talk about, what's the other thing, emission spectras and all that, star spectras. There's more to you with the playlist below. So, stay curious, and also, try and learn as much as you want about the universe as we go. And yeah, have a good day.